Let us look at an example of transportation problem where some of the possible routes may not be available for use due to reasons like unfavorable weather conditions or damaged road conditions or some local political conditions or strike on a particular route, etc. etc. So let us take a look at this example and see how we can solve this to get an optimal transportation route. A company has three factories which supply their products to four warehouses. Monthly capacities of the factories are 120, 200, and 180 units respectively. The monthly requirements of warehouses are 100, 140, 110, and 120 respectively. Now we have also been given the unit shipping cost. So what this means is for shipping one unit of material from factory 1 to warehouse P, it costs 15 rupees. Similarly, for shipping one unit from factory 1 to warehouse R, it costs 30 rupees. Now this dash here means that we cannot transport material from factory 1 to warehouse Q because this route is prohibited. So shipment from 1 to Q, that is 1 to Q, 2 to P, so this one here, and 3 to R, so this one here, is not possible due to certain unavoidable reasons. Find the optimum distribution program to minimize the shipping cost. So let us understand this example in more detail. So let's say the first factory is located in India and it has a supply capacity of 120 units per month. So supply capacity is 120 units per month. Let's say the second factory is located in Western China. Now it has a capacity of 200 units per month. So supply capacity is 200 units per month. And the third one is located in the other side of China, that is the eastern side of China. So let's say this is the third factory here. Now this one has a supply capacity of 180 units per month. Now there are four warehouses to which the material has to be transported. So let's say the first one is here. This is P, this is Q, this is R, and this is S. Now the demand at P is 100 units per month. So demand is 100 units per month. For Q, demand is 140 units per month. For R, the demand is 110 units per month. And for S, it is 120 units per month. Now for shipping material from factory 1 to warehouse P, the cost given to us is 15 rupees per unit. So this is 15 rupees per unit. The transportation of material from factory 1 to Q is not possible due to some unavoidable circumstances. Let's say there is some political conditions developed in the countries through which this route passes, or some other weather conditions are there. So for now let's skip this route. From factory 1 to R, the unit cost is 30 rupees per unit. So 30 rupees per unit. And from 1 to S, the unit cost is 20 rupees per unit. So this is 20 rupees per unit. So with this information given to us, we have to find out the optimum distribution program to minimize these shipping costs. So let's find out how we can use the transportation model to solve this problem. So the first step in solving the transportation problem is the formulation of a transportation table. In this step, we have to express the supply from origins, requirements at destination, and cost of shipping from origin to destination in the form of a matrix. So on the left hand side of the table, I'll place the origin of supply, which are the factories. So factories are 1, 2, and 3. And on the right hand side of the table, I'll place the capacity of these factories, which is in units per month. Now the first factory has a capacity of 120 units per month, the second one has 200 units per month, and the third one is 180 units per month. Now on top of the table, we'll place the warehouses. So the four warehouses are P, Q, R, and S. And at the bottom of the table, we'll place the demand at these warehouses. So P has a demand of 100 units per month. Q has a demand of 140 units per month. R has a demand of 110 units per month, and S has a demand of 120 units per month. This is again units per month. Now in these boxes, we have to place the unit cost of shipping. So from 1 to P, the unit cost is 15. For 1 to Q, the unit cost has not been given because it is a prohibited route. For 1 to R, the unit cost is 30. And from 1 to S, it is 20. From 2 to P, the route is prohibited. 2 to Q, it is 24. 2 to R, it is 12. And 2 to S, it is 15. 3 to P is 25. 3 to Q is 15. 3 to R is prohibited. And 3 to S is 20. Now, we don't have the unit shipping cost for 3 of the routes. However, the transportation model assumes that items should be transported conveniently from all sources to all destinations. That means that we should have a cost associated with each and every route. Now these 3 routes are prohibited. That means these 3 routes should not be allocated for any material to be transported. And that can be achieved if we assign a infinitely large value of cost for these 3 routes. And since this is a minimization problem, basically the transportation model will try to avoid these routes because the cost is the highest. So let's place a cost of infinity here, which indicates that this has an infinitely large cost of transportation. Same with this one here, 2 to P, and same thing for 3 to R. Now once the transportation table has been created, a check needs to be done to find out if the total supply and demand are equal. If yes, the problem is said to be balanced, and if not, a dummy origin or destination is added to balance the supply and demand. So let's add up the supply capacities first. So 120 plus 180 is 300 plus 200 is 500. Now let's add up the demand. So 100 plus 140 is 240 plus 110 is 350 plus 120 is 470. So the total supply is 500 while the total demand is 470. Now one of the assumptions in the transportation model is that the total quantity of material available at different sources should be equal to the total requirement at different destinations. So in order to meet that criteria, we'll have to add a dummy source of demand so that we can make the total demand and total supply equal to each other. So let me modify this transportation table to add a dummy source of demand. So let's call this column as D for dummy, and this will have a demand of the difference between the total supply and total demand. So earlier our total supply was 500 while the total demand was 470. So 500 minus 470, which is 30, is the differential. So we'll add 30 here as additional demand. Now we need to associate a cost with this dummy destination. So basically what is happening here is that these three plants have a supply capacity of 500 units per month, while the demand at these warehouses is equal to 470 units per month. So what is happening is these factories are producing 500 units and then will be shipping only 470 units because that's the demand at these warehouses. So these 30 units which will be produced in these factories will actually not be shipped out of these factories and will be kept in its inventory. So since these 30 units are not going to be shipped, we'll assume the cost of shipping as 0. And then let me add the capacities here, which is in units per month: 120, 200 and 180. So now the total of supply and total of demand becomes equal, which is 500. Now after we have created the transportation table, the next step is to establish the basic initial feasible solution, and we'll use the Vogel's approximation method to achieve that. Now the first step in Vogel's approximation method is to calculate the difference between the two minimum elements for each row and each column, or basically we are trying to find out the penalty cost for each row and each column. So for the first row, the lowest is 0 and the next lowest is 15, so the difference is 15. For the second row, lowest is 0 and the next lowest is 12, so 12 minus 0, 12. For the third row, the lowest is 0 and the next lowest is 15, so 15 minus 0, 15. Now let's do the same for the columns. So for the first column, the lowest is 15 and the next lowest is 25. So 25 minus 15 is 10. For the second column, it will be 24 minus 15, which is 9. For the third column, it will be 30 minus 12, which is 18. For the fourth column, it will be 20 minus 15, which is 5. And for the fifth column, it will be 0 minus 0, which is 0. Now next we have to select the row or column with the largest difference. So R has the largest difference. So let's select this column R. Now we have to allocate the maximum number of units to the square with the minimum cost in this selected column. So the square with the minimum cost is 2 to R, this one here. So let's evaluate the supply and demand situation here. So factory number 2 has a supply capacity of 200 units per month, while warehouse R has a demand of 110 units per month. So the maximum we can allocate here is 110. So with this allocation, now the capacity remaining at factory number 2 is 200 minus 110, which is 90 units, while the demand at warehouse R becomes 110 minus 110, which is 0. Now, since all the demand at R has been completely met with this allocation, let's cross off the remaining squares for this column R, indicating that they are no longer available for allocation. Now let's redetermine the row and column differences. So for the first row, again lowest is 0, next lowest is 15, so the difference is 15. For the second row, it is 15 minus 0, which is 15. For the third row, again 15 minus 0, which is 15. Now let's do the same for the columns. So first column, 25 minus 15, which is 10. Second column, 24 minus 15, which is 9. Third column is completely allocated, so we'll skip this one. Fourth column, 20 minus 15, which is 5. And fifth column, 0 minus 0, which is 0. Now let's find out the row or column with the largest difference. So here we have a tie between factory 1, 2 and 3. So let's choose any one arbitrarily. Let's choose the first factory. Now let's try to allocate the maximum number of units to the square with the minimum cost in this row. So the square with the minimum cost is this 1D. Now let's evaluate the supply and demand situation. So D has a demand of 30 units while 1 can supply 120 units. So the maximum that can be allocated is 30. Now with this allocation, the remaining demand at D becomes 0, while the remaining supply at 1 becomes 120 minus 30, which is 90 units. And now since the entire demand at D has been met, we'll cross off the remaining squares, indicating that they are no longer required to be allocated. Now let's redetermine the row and column differences. So for the first row, the lowest is now 15 and the next lowest is 20. So the difference is 20 minus 15, which is 5. For the second row, the lowest is 15 and the next lowest is 24. So the difference is 24 minus 15, which is 9. For the third row, the lowest is 15 and the next lowest is 20. So the difference is 20 minus 15, which is 5. Now for the first column, the difference is again same, 10. For the second column, again the same, 9. Third column we can skip as it is completely allocated. Fourth column, difference is again same, 5. And for the fifth column, since it is completely allocated, we'll skip it. Now let's find out the row or column with the largest difference. So the largest difference is for warehouse P. So for this column P, now we have to allocate the maximum number of units to the square with the minimum cost. So the square with the minimum cost is this 1P. Now let's evaluate the supply and demand situation. So factory 1 has a supply capacity of 90 units per month, while P has a demand of 100 units per month. So the maximum that can be allocated is 90 units. So with this allocation, the entire supply has now been exhausted. So the remaining supply capacity is 0. And the remaining demand at P becomes 100 minus 90, which is 10. Now since the entire supply capacity at factory 1 has been exhausted, let's cross off the remaining boxes, indicating that they are no longer available for allocation. Now let's redetermine the row and column differences. So the first row is now completely allocated, so we can skip it. For the second row, the lowest is 15 and the next lowest is 24. So 24 minus 15 is 9. For the third row, lowest is 15 and the next lowest is 20. So the difference is 20 minus 15, which is 5. Now for the first column, the lowest is 25 and the next number that we have is infinity, which is an imaginary number which we have placed. So since we can't calculate the penalty cost here. We'll skip this column. For the next column, 24 minus 15, which is 9. For the third column, all the allocation has been made, so we'll skip it. The fourth column, 20 minus 15, which is 5. And fifth column we can skip as it is also allocated. Now let's determine the row or column with the largest penalty cost. So we have a tie between row number 2 and column Q. So there is a tie here. Now let me try to find out which of these two will give more chance of allocation, or in other terms, which of these two will give more units to be allocated and what will be the cost. So for row number 2, if we select this, then the square with the lowest cost is this one here, 2s, which has a cost of 15. And if we select column Q, then the lowest is 3Q, which is again having a cost of 15. So both will give us the same cost, so that is also a tie. Now let's find out which will give us the capability to allocate more units. So for 2s, this one here, we'll be able to allocate 90 units because 90 is supply and 120 is demand. While if we select this square here, 3Q, then we'll be able to allocate 140 because 140 is the demand and 180 is the supply. So since column Q gives us capability to allocate more units at the same unit cost, let's select column Q here. So as we already determined, we can allocate 140 units to this square. So with this allocation, the remaining supply capacity at factory number 3 becomes 180 minus 140, which is 40 units, while the remaining demand at warehouse Q becomes 140 minus 140, which is 0 units. Now since the entire demand at Q has been met with this allocation, we'll cross off the remaining squares indicating that they are no longer required to be allocated. Now let's redetermine the row and column differences. So for the first row, it is already allocated, so we'll skip it. For the second row, differences between infinity minus 15. Since this is an imaginary number, we'll skip this row as well. For the third row, differences between 25 and 20, which is 5. Now for the first column, again infinity minus 25, so we'll skip it. Second column also we'll skip as it is completely allocated. Third column is also completely allocated, so we'll skip it. Fourth column, difference is between 20 and 15, which is 5. And the fifth column we'll skip as it is completely allocated as well. So now let's determine the row or column with the largest difference. So we have a tie between row number 3 and column S. Now let's compare these two options. So row number 3 gives the lowest unit cost as 20, while column number S gives us the lowest unit cost of 15. So let's choose column number S first. Now for this square 2S, which has the lowest unit cost of 15, let's evaluate the supply and demand situation. So factory number 2 has a supply capacity of 90 units, while warehouse S has a demand of 120 units. So the maximum we can allocate here is 90 units. Now with this allocation, the supply capacity remaining at factory number 2 becomes 0, while the remaining demand at S is now 120 minus 90, which is 30. Now since the entire supply capacity at factory number 2 has been exhausted, let's cross off the remaining boxes indicating that they are no longer available for allocation. So with this allocation, now we have only one row remaining which has two squares which have not been allocated. So out of the two squares, let's choose the one with the lower unit cost, which is 3S. Now let's evaluate the supply and demand situation here for this box. So factory number 3 has a supply capacity of 40 units, while warehouse S has a demand of 30 units. So the maximum we can allocate here is 30 units. So now with this allocation, the capacity remaining at factory number 3 becomes 10, while the demand at S becomes 0. Now all the demand for S has been met, and if you check, all these squares for column S are either allocated or crossed off. So we are good here. Now the last square to be allocated is 3P. P has a demand of 10 units, while 3 has a capacity of 10 units as well. So we can allocate 10 units to this square. Now with this allocation, the entire demand at P has been met, and the entire supply capacity for 3 has also been exhausted. So this becomes our basic initial feasible solution, as all the demand and all the supply has been allocated. And a quick observation indicates that we have been able to avoid allocations to these routes which were prohibited, like 1Q, 2P, and 3R. And the differential in the supply and demand that we had of 30 units has been allocated to the dummy source of demand, which has a cost of shipping of 0, indicating that these 30 units will be produced by factory 1 but will be stored in the inventory for future use. Now let's calculate the total cost of transportation that we have achieved using this method. So the total cost will be the multiplication of the unit cost of shipping and the number of units shipped. So 90 multiplied by 15 plus 30 multiplied by 0 plus 110 multiplied by 12 plus 90 multiplied by 15 plus 10 multiplied by 25 plus 140 multiplied by 15 plus 30 multiplied by 20. So this is equal to, let me pull my calculator here. So 90 multiplied by 15 plus 30 multiplied by 0 plus 110 multiplied by 12 plus 90 multiplied by 15 plus 10 multiplied by 25 plus 140 multiplied by 15 plus 30 multiplied by 20. So 6970 is the total cost of transportation. Now once we have found out the initial basic feasible solution, let's now find out if this is the optimal solution or is there any scope for further reduction in the total cost of transportation. So let me redraw this transportation table with the initial feasible solution, and then we'll perform the optimality test. Now this is the basic initial feasible solution with the allocations. Now before we proceed with the optimality test, we have to first find out if this basic initial feasible solution is acceptable to proceed with the optimality test or not. Now there are two conditions for testing for acceptability. The first one is that the allocations should be equal to m plus n minus 1. M is the number of rows, n is the number of columns. So here we have 3 rows and 5 columns. So this is 5 plus 3, 8 minus 1, which is 7. And let's count the number of allocations. So we have 1, 2, 3, 4, 5, 6, and 7. So the number of allocations is equal to m plus n minus 1. So this condition has been met. And the second condition is that the allocations should be in independent positions. What this means is that if we create a closed path for any of these allocated squares, then it is impossible to travel from this allocated square back to itself by a series of horizontal and vertical jumps from one occupied cell to another without a direct reversal of the route. So let's try creating a closed path for the first allocated square, which is 1p. So from here we can go to this square, then to 3q, then we can go to 3s, then from here we can go to 2s. Now from 2s we can only go back to 2r, but from here we can't jump to 1p using horizontal and vertical lines because there is no other allocation, so we can't go back to 1p without actually reversing this route. So what that means is that this allocation is an independent position, and if you check, all the other allocations are also similar, that is, they are also in independent positions. So this means that the second condition has also been met, and now we can proceed with the optimality test. So to perform the optimality test, let's use the modified distribution method. So the first step in the modified distribution method is to set up a cost matrix containing the unit costs associated with the cells for which allocations have been made. So let's create that table. So on the left hand side we have the factories. So 1, 2, 3, and on the top we have the warehouses. So P, Q, R, S, and D. Now in this middle boxes we have to place the unit cost of the cells which have allocations. So for example, the first box 1p, the unit cost is 15, so we'll place 15 here. The second is 1d, we'll place the unit cost which is 0. For the second row, for 2r, 110 is the allocation and 12 is the unit cost, so we'll place 12. For the second row again, for the square 2s, 15 is the unit cost. Now for third row, 25, 15 and 20. Now the next step is to assign the variable ui to each of the rows and vj to each of the columns. So u1, u2, u3, and v1, v2, v3, v4 and v5. Now the next step is to compute the values of u and v for the allocated squares such that ui plus vj is equal to cij, and cij is the unit cost that has been noted in this matrix. So for the first square, u1 plus v1 is equal to 15. For the second one, u1 plus v5 is equal to 0. Next is u2 plus v3 is equal to 12. u2 plus v4 is equal to 15. u3 plus v1 is equal to 25. u3 plus v2 is equal to 15, and u3 plus v4 equals to 20. Now we have to find out the values of ui and vj using these equations. Now since we have m plus n variables, that is, we have 1, 2, 3, 4, 5, 6, 7, 8 variables. However, we have only 7 allocations. So what we do is that we will assume that one of the variables has a value of 0. So let's assume that v1 is 0. So using this now, let's try to find out the values of ui and vj. So here v1 is 0, so u1 equals to 15 and v1 is 0. Now u1 is 15, so v5 becomes 0 minus 15, which is minus 15. So u1 is 15 and v5 is equal to minus 15. Now this equation here, u2 plus v3 equals to 12. So we don't have the value of either u2 or v3. So let's skip this one for now. Same with the next one, u2 plus v4 is 15. We don't have any of the values. The next one, u3 plus v1 is 25. So now for this equation, u3 plus v1 equals to 25. We have the value of v1, which is equal to 0. So u3 becomes 25 and v1 is 0. Now again, the next equation, we don't have the value of u3 or v2. Let's skip to the next one. u3 plus v4 is 20. Here we have the value of u3, which is 25. So u3 equals 25 and v4 becomes 20 minus 25, which is minus 5. Now using this value of v4, let's try this equation. u2 plus v4 is 15. So v4 is minus 5. So u2 becomes 15 plus 5, which is 20. So u2 is 20 and v4 is minus 5. Now u2 is 20, so we can use it in this equation. So v3 becomes 12 minus 20, which is minus 8. So u2 is 20 and v3 is minus 8. Now for this equation, u3 plus v2 is 15. We can use the value of u3 is 25. So v2 becomes 15 minus 25, which is minus 10. So u3 is 25 and v2 is 15 minus 25, which is minus 10. So now let me recreate this matrix and let me place these values of ui and vj's. So in this matrix, what I've done is I have placed the cost of the stone squares in black color, that is the squares which have allocations, and the cost of the water squares in red color, that is the squares which do not have allocations. And I have also placed the value of ui's and vj that we had achieved in the last step. Now the next step is to calculate the net cost change for each of the water squares, that is the squares without any allocations. Now for the water squares, ui plus vj is known as the implicit cost and cij is known as the actual cost of the cell, and the net cost change is calculated as cij minus ui plus vj. So let's try to calculate the net cost change value for each of the water squares. So the first water square is 1q. Cij value is infinity minus ui is 15 and vj is minus 10. So since this has an infinity number, let's leave that as it is. The next water square is IR. Cij is 30, which is this value here. Ui is 15 and Vj is minus 8. So 15 minus 8 is 7 and 30 minus 7 is 23. The next water square is IS. Cij is 20, Ui is 15 and Vj is minus 5. So 15 minus 5 is 10 and 20 minus 10 is 10. The next water square is 2p. Cij is infinity, ui is 20, vj is 0. So let's skip this as this has this infinity number here. The next water square is 2q. Cij is 24, ui is 20, vj is minus 10. So 20 minus 10 is 10 and 24 minus 10 is 14. The next water square is 2d. Cij is 0, ui is 20 and vj is minus 15. So 20 minus 15 is 5 and minus sign outside the bracket, so minus 5. Now the next water square is 3r. So this has a Cij value of infinity and minus ui is 25 plus vj is minus 8. So this becomes 25 minus 8, but we have infinity in this whole equation, so let's skip this value. The next water square is 3d. Cij is 0, ui is 25, vj is minus 15. So this becomes 25 minus 15, which is 10, and there is a negative sign outside, so minus 10. Now the next step is to evaluate the solution for optimality by reviewing the sign of the net cost change values. If all the values are positive, then the optimal solution has been reached. However, we have these two values here with negative sign of the net cost change value, which indicates that we have not yet reached the optimal solution and there is some scope for further improvement. So now we'll try to improve the existing basic initial feasible solution to arrive at an optimal solution. So the first step for iterating towards optimality is to select the water square with the largest negative net cost change. So the square with the largest negative net cost change in our case is 3d with a value of minus 10. So let me draw the transportation table again and then we'll iterate towards optimality. So this is the basic initial feasible solution that we have to improve upon and iterate towards optimality. So the water square with the largest negative net cost change was 3d, which is this one here. So let me create a closed path for this square. Now this closed path has to be created using rectilinear motions, that is moving horizontally and vertically only. You have to start from the selected water square and move via the stone squares and then back to the same water square. A right angle turn can be made only at the stone square, even though the path may skip over stone and water squares. So for this square 3D, the closed path is 3D to 3P to 1P to 1D and then back to 3D. Now we have to assign alternate positive and negative signs, starting with a positive sign at the selected water square. So basically what we are trying to do here is that in the previous step we found out that if an allocation is made to the square 3D, then the net cost change is negative, meaning that the overall transportation cost is going to reduce. So now we are trying to make an allocation to this square. However, we have to balance it out for the demand and supply constraints so that they are not violated. So this plus sign indicates that we have to add an allocation here, and to balance it out we have these alternate plus and minus signs for the other squares. Now we have to determine how much can we allocate to this square 3D. So we have to subtract the smallest of the figures from each square at the negative sign on the closed path. So the maximum we can subtract is 10 because we can't have a negative value. So we can add 10 to 3D, subtract 10 from 3P, add 10 here to 1P, and subtract 10 from here, which is 1D. So this becomes our new improved solution. So let me re-establish these new allocations and then we'll test for optimality. So now for this improved solution, let's try to find out the total cost. So this is 100 multiplied by 15 plus 20 multiplied by 0 plus 110 multiplied by 12 plus 90 multiplied by 15 plus 140 multiplied by 15 plus 30 multiplied by 20 plus 10 multiplied by 0. So let me pull my calculator to calculate this. So 100 multiplied by 15 plus 20 multiplied by 0 plus 110 multiplied by 12 plus 90 multiplied by 15 plus 140 multiplied by 15 plus 30 multiplied by 20 plus 10 multiplied by 0. So it is 6870. So in the previous solution that we had, that is the basic initial feasible solution, the total cost was 6970 rupees, and after the first iteration we have brought down the cost to 6870 rupees, which is a saving of 100 rupees. Now let's find out if this is an optimal solution or not. So before we proceed with the optimality test, we have to do the acceptability test to find out if we can proceed with the optimality test or not. So the first condition is that number of allocations should be equal to m plus n minus 1. So m plus n is 3 plus 5, which is 8, and minus 1 is 7. And let's now count the number of allocations. So 1, 2, 3, 4, 5, 6, 7. So the number of allocations is equal to m plus n minus 1. So the first condition has been met. Now the next condition is that all the allocations should be in independent positions. So if you check, you'll find that all the allocations are in independent positions. So now let's proceed with the optimality test. So the first step in the optimality test is to set up a cost matrix containing the unit costs associated with the cells for which allocations have been made. So let's draw that cost matrix. So on the left hand side we have the factories 1, 2 and 3, and on the top we have the warehouses P, Q, R, S and D. So the first one is 15, then 0, then 12, 15, 15, 20 and 0. Now the next step is to assign UI and VJ. So U1, U2, U3, V1, V2, V3, V4, V5. The next step is to compute the value of U and V. Here we are assuming that V1 equals to 0, and we have to compute in a way that UI plus VJ is equal to Cij. So U1 plus V1 equals to 15, U1 plus V5 equals to 0, U2 plus V3 equals to 12, u2 plus v4 equals to 15, u3 plus v2 equals to 15, u3 plus v4 equals to 20, and u3 plus v5 equals to 0. Now since v1 is 0, u1 equals to 15. Now u1 is 15, so v5 becomes 0 minus 15, which is minus 15. Now we can't solve the third equation because we don't have any of the variables. Fourth is the same case. Fifth is also the same case. Sixth is also the same case. But seventh, we have the value of v5, which is minus 15. So u3 becomes 0 plus 15. So u3 equals to 15 and v5 equals to minus 15. Now using the value of u3 here in this equation, so u3 equals to 15 and v4 becomes 20 minus 15, which is 5. Now in this equation again, u3 equals to 15 and v2 becomes 15 minus 15, which is 0. Now in this equation, v4 is 5, so u2 becomes 15 minus 5, which is 10. Now since we have the value of u2, so v3 becomes 12 minus 10, which is 2. So u2 is 10 and v3 is 12 minus 10, which is 2. So after we have found out the values of ui and vj, the next step is to calculate the net cost change value for each of the water squares. So let's proceed to perform that step. So in this matrix, I have placed the unit cost value of the stone squares in black color and the unit cost value of the water squares in red color. Also, I have placed the value of ui and vj that we had obtained in the previous step. Now we need to find out the net cost change value for the water squares, that is the squares with these numbers in red color. And the net cost change value is found by using the formula Cij minus ui plus vj. So the first water square is 1q. Now Cij is infinity minus ui is 15 plus vj is 0. Since this has an infinity value, let's skip it. The next water square is 1r. Cij is 30, ui is 15 and vj is 2. So 15 plus 2 is 17 and 30 minus 17 is 13. The next water square is 1s. Cij is 20, ui is 15 and vj is 5. So 15 plus 5 is 20, 20 minus 20 is 0. The next water square is 2p. Cij is infinity, ui is 10, vj is 0. So let's skip this because this has an infinity value. The next water square is 2q. Cij is 24, ui is 10, vj is 0. So 10 plus 0 is 10, 24 minus 10 is 14. The next water square is 2d. Cij is 0, ui is 10, vj is minus 15. So 10 minus 15 is minus 5 and there's a negative sign outside the bracket. So this becomes plus 5. The next water square is 3p. Cij is 25, ui is 15 and vj is 0. So 25 minus 15 is 10. And then last water square is 3r. Cij is infinity, ui is 15, and vj is 2. So let's skip this because this also has an infinity value. So now let's evaluate the solution for optimality by reviewing the sign of the net cost change value. So here all the water squares have a positive net cost change value, which indicate that if any allocation is made to these cells, then it will not reduce the total cost but increase the total cost. So the last solution that we got, where the total cost was 6870 rupees, is our optimal solution.